Okay, just want to do a little bit of qualitative analysis here for our differential equations that correspond to forced harmonic oscillators. Just a reminder, the mathematical tools that we've been using here would work for any equation of this type regardless of the values of P and Q. However, if we're talking about a harmonic oscillator, it will always be the case that Q is positive, and P will be positive unless we have an undamped system. But most often, P and Q are both going to be positive if we have a harmonic oscillator that is not undamped. So we don't suspend the laws of physics. There is friction, there is air resistance. Okay, so those would both be positive. Now, I know that my general solution is just the sum of y sub h plus y sub p, a solution to the associated homogeneous equation and my particular solution. But if P and Q are both positive, so that I have a damped harmonic oscillator, I know that this, as t goes to infinity, these solutions are going to go to zero. Remember, when we looked at the corresponding system, we saw that we always had a sink. Sometimes a spiral sink, sometimes just a plain old regular sink, but it was always a sink. So these solutions are going to be going to zero. So as time goes to infinity, all of my solutions are going to approach my particular solution. Now, there are infinitely many particular solutions, but they all differ from each other by one of these guys, which goes to zero as t goes to infinity. Okay, so they're all approaching the same basic curve. We call y sub p, we call that the forced response, because it's what's due to the fact that we introduced this forcing function. We also call it the steady state response. And that's because of this fact right here, that all solutions are going to approach that as time goes off to infinity. Initially, for small values of time, this might not yet be small. So my solutions could look very, very different initially based on different initial conditions. But as time goes off to infinity, it's the particular solution that all of these are going to be approaching, so that the end behavior for all of my solutions is going to be the same. Steady state is different from equilibrium. It doesn't have to be constant. What I'm saying is that all of my solution curves are going to look like the same function eventually. Not necessarily a constant function, but the same function, regardless of what initial condition I have. Pretty interesting. Okay. Just one more quick vocabulary word. We call this the natural response. So solutions to the associated homogeneous equation are the natural response. That's what we get just due to the forces of nature of the restoring force and the damping forces. Okay, this is the forced response because we introduced an additional force. Again, remember thinking of giving Moose a push on that mass so that he can have a slightly more exciting ride. Okay, that's it for this section.